So far, listen, so far we have a pretty good idea of how this thing works. I mean, if you think about it, what do we have here? We have this electron gun. That's wherever my electron gun is. We have this electron gun here, and it's shooting out this beam of electrons. They strike the phosphor coating on the front of the screen. That causes the phosphor to glow. But really, all we'd end up with is a dot right in the middle of the screen. So somehow we need to scan that back and forth. And of course, we use the deflection coil that's in the yoke and the deflection circuits that drive it, which we'll look at in great detail later on, to make the beam scan, making the raster. Then all we have to do is turn the electron gun on and off at the right times to make the video image on the front of the screen. And the synchronization takes over to keep everything solid locked in place. So we have a pretty good idea of how the thing works now. We only have to look at one more thing before we can really determine how the monitor, or really know how the monitor actually works. Let's go back to the picture tube itself. So here's the CRT. Has a nice thick glass front on it. The 3 cathodes down here. And of course, it does have that heater in there, which we're going to talk more about in detail later on as well. The front of the monitor, the glass of the front of the monitor is really, really thick, but it's probably not thick for the reason you think it is. You probably think that it's really thick so that if you hit it with a brick or something, it doesn't explode or implode, but that's really, I mean, that's part of it, but that's not really why it's really thick. This glass that the CRT is made of is leaded glass. There's a tremendous amount of lead in the glass. And the reason it has lead in the glass is that if it did not have lead in the glass, the monitor picture tube would be an X-ray machine. Even if the monitor is working perfectly normally, there would be X-rays coming out of the picture tube. So there's a lot of lead in that glass. And the reason I'm mentioning it is twofold. Number one, we're going to be talking a lot about X-rays later on in the class, because there's a certain very common failure in a monitor that can cause it to emit a whole bunch of X-rays regardless of the leaded glass, and we'll talk about that later on. The other reason I mentioned it to you, though, a couple of other reasons. One is that because of the lead in the glass, it is really soft. You should never turn a monitor face down on your workbench unless you have something soft on the workbench. Now, naturally, if you have a touch screen on it, as this one does, that's not leaded glass, and that's harder, much harder glass than the picture tube. But if you're actually working on a picture tube without a touch screen, and now that I think about it, there's hardly any of those unless you're changing touch screens. If you put it face down on your workbench and kind of scoot it around, you'll burnish a fuzzy kind of a dot right in the middle of the screen since it's convex. It's just a little dot right in the middle of it, and that's kind of bad. Anyway, so we have this really thick glass front, and the way it works is that the electrons shoot out of the electron gun. And these little, remember, they're little negatively charged electrons. And they are really hauling buns. They are just moving really fast. And again, when these electrons, which are moving really fast, strike the phosphor coating on the front of the screen, that's what makes the phosphor glow. That change of mechanical energy into light energy like that. Well, after the electrons strike the front of the picture tube, the electrons do not come out of the CRT. They don't come out of the CRT because the CRT is made out of glass, and glass is an insulator, and electrons cannot go through glass. Anyway, if they did, you'd probably sterilize all your customers. You probably wouldn't want to do that. Or maybe you would. I don't know. Your customers, I don't know your customers as well as you do. Most of them are beyond breeding age anyway, so it doesn't make any difference. So there you go. Joke. All right. No, but seriously, what really happens, though, is this. The electrons strike the front of the screen, and then they bounce off inside, like this. Well, if we can't really allow those electrons to stay inside the picture tube. If we allow the electrons to remain inside the picture tube, they will quickly, within a fraction of a second, really, form a large negatively charged cloud down here in the bell of the CRT. Well, you can imagine what would happen now, because we have this stream of electrons that's trying to get out of the electron gun and whack against the front of the screen, and it has to do it at practically the speed of light. Remember, too, as I mentioned just a little while ago, that if we have two of the same polarity, they repel each other, don't they? Just like two of the same poles of a magnet do. So if we have this negatively charged cloud here, as the electron beam comes out of the electron gun, it's going to be repelled by this big negatively charged cloud down here, and the electrons won't be able to reach the front of the screen, and if they can't whack against the front of the screen, you won't see any brightness at all on the front of the picture tube. So somehow we have to get rid of these spent electrons after they've struck the front of the screen. And this is where the high voltage comes in a monitor. I think most of you are aware that there's some kind of high voltage somewhere in a monitor, and that's really probably why you're here, because you're scared shortless to work on a monitor because you don't know what you can touch and what you can't touch and so on. Well, here's what the high voltage is for. On the top of the CRT, there's a connector right there, and it's referred to as the second anode. It's called the second anode. An anode is something that attracts electrons. Cathodes emit electrons. We've looked at the cathodes already. This is an anode. An anode attracts electrons. For those of you that are somewhat familiar with diodes, you know that a diode has an anode and a cathode. Technically speaking, that's the deal. An anode is something that attracts electrons. A cathode is something that emits electrons. So on the top of the picture tube, we have this thing called the second anode, and I'm going to take that cover off in just a second and show you what's inside in just a second. The second anode is a metal plug that is molded right into the glass of the picture tube. It is not a hole going into the picture tube. It's all sealed up because this is a vacuum tube. There is no air inside the picture tube. There can't be any air inside the picture tube because, remember the CRT heaters down here. The CRT heater that heats up the cathode in order to get it to emit electrons. There can't be any oxygen inside the picture tube because if there was, it would burn up the heater. In addition to that, really there can't be any gas really at all inside the picture tube, because if there was any gas inside the picture tube at all, as if there were any kind of molecules of gas floating around inside here, as the electron beam comes out of the electron gun, it would strike those molecules of whatever gas it is inside, and it would ionize them and cause them to glow on the inside of the picture tube. Well, we don't want to glow on the inside of the picture tube. We only want it to glow on the outside of the picture tube. If you ever fire up a monitor and you look down in the neck of the picture tube and you see kind of a purple glow down in there, it's kind of a beautiful indigo purple kind of a glow down in there, you have a gassy picture tube. That is to say, air has gotten into the picture tube. It's dead. You can't fix it. It's completely gone. You have to throw the picture tube away. Typically, it's accompanied by some arcing and sparking and stuff down there, and so it's usually pretty obvious that you have a bad CRT. But regardless of that, so we have this second anode, and so the second anode is a metal plug that's molded into the glass of the picture tube. But it's not a hole, because if it was a hole, it would let air into the picture tube, and we don't want to do that. Or as one student would try to convince me, it would let the vacuum out, right? So we don't want to let the vacuum out, so we're going to have that all sealed up. Now, coating the inside of the picture tube, painted on the inside of the bell of the CRT, there's a conductive substance known as Aquadag. A-Q-U-A-D-A-G, Aquadag. It's called Aquadag because what it really is, you don't have to know this part, what it really is when they first make it is a mixture of water and graphite. Graphite, as you probably know, conducts electricity really well. Graphite is like pencil lead. So imagine taking a fine bit of ground up pencil lead, mixing it up with water to make what they call a colloidal suspension, a slurry of this stuff, and then they spray it on the inside of the picture tube before they put the picture tube together. They spray it on the inside. And that Aquadag is touching the second anode. In other words, if I electrically connect to that second anode connector there, I am electrically connected to the whole inside of the picture tube. Is everybody with me on the concept there? Now, there's aquadag on the outside of the picture tube as well. Let's take a look at it, shall we? And that's this grayish substance that you see right here. Here's where the aquadag is not. This is just glass here. And here, this gray part is where you see the aquadag is. The aquadag on the inside is not connected to the aquadag on the outside, though. The aquadag on the outside is always grounded. You will always see what's known as the CRT ground surrounding the picture tube. You'll notice that there's a spring. See the spring down there? Right there. That holds it taut. And then there's this cable. It's kind of hard to see on this monitor. This cable that surrounds the whole picture tube. Let's see if I can show you. Here's a better look at it here. There. Can you see the metal strap right there? It's attached to the spring. That's the CRT ground. And it surrounds the whole picture tube. Well, that CRT ground is always connected to a black wire that goes up to the neck board of the CRT. In other words, here's the CRT ground, this wire that you see here. And if you look carefully, I'm going to tug on the wire. See how I'm moving the spring? Right? Let me turn on some light. See that black wire that's attached to it right down there? If I pull on that, right? And that black wire is always connected to the neck board. And that's this one right here, CRT ground. It just unplugs, plugs right back in. When you reconnect the monitor, after pulling the chassis off, make absolutely sure that you put the CRT ground on there. If you fail to put the CRT ground on there, it may work perfectly okay, but what may happen is it will build up a big static charge. And about every 30 seconds or a minute or so, you'll hear a snap of a spark as it kind of discharges to ground somewhere. If you don't give that static electricity someplace to go to ground, it finds its own place, and that place may be through you, actually. As you approach the monitor, you may get a spark to jump to your hand. Ever have that, Ray? More than once, huh? And then you go, oh, CRT ground's not hooked up. So the outside, the CRT ground is grounded to the neck board. The second anode is connected through this real thick red wire that you see here down to the high voltage unit in the monitor, which is this thing right here. The high voltage unit, also known as the flyback or the flyback transformer. Really thick red wire here. And that's connected to the high voltage unit, which is also known as the flyback or the flyback transformer, for reasons that you'll find out later on. Now, this looks like a really thick red wire, but it's actually not. It's a really thin wire with a shitload of insulation on it. And it has a mess of insulation on it because the high voltage unit creates approximately 20,000 volts or so. It really depends on the physical size of the picture tube. It's approximately 1,000 volts for every diagonal inch. I don't measure it very often. But, in a 17-inch monitor, it's, 17,000, 18,000 volts. In a 19-inch monitor, 20, 22,000 volts, and so on. The bigger the monitor is, the higher that high voltage is. And it is direct current. It's DC, and it is positive. Never, ever, 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 under any circumstances, ever cut and splice that wire. I have absolutely no idea why anyone would do such a crazy thing, but I've seen it way more than once where someone has chopped the second anode wire and somehow spliced it together and wrapped 100 layers of black electrical tape on the thing to try to insulate it. Well, that just doesn't work. No matter what kind of black tape you use, even if you're using something really good like Scotch 33 Plus or some really good black tape, the insulating strength of this, the dielectric strength as it's called, is only 600 volts. I don't care how many wraps of wire you put on that second anode, you're not going to insulate it properly. There's no reason for you to cut it and splice it. I have to assume it's because somebody was paranoid about disconnecting it or something and couldn't figure it out, but it's not too difficult, as I'll show you in just a minute here. In fact, there's no time like the present here. Let me just show you what the second anode actually looks like inside here. And here's the actual second anode itself. And you can see that it's completely sealed because, remember, we don't want to let the vacuum out, right? So it is completely sealed up inside. No, it's not. Right? Also, on this second anode connector, as long as I have it off, I might as well show you. When you put the second anode connector back in there, it's important to get both of these little fingers in place. There's two little fingers here that actually go into the second anode, and it's important to get those in there properly. The best way to do that is, in my opinion, is to kind of hold the thing back like this, and then you kind of put in one side, and then some people would use a screwdriver to push in the other. If you're experienced, you don't need to do that, but kind of push it over like that, and put the other one in. And when you get it in there, make sure that it's in there. And by virtue of the fact that we have this high voltage hooked up to the second anode, the whole inside of the picture tube is now charged at, let's say, plus 20,000 volts DC. Is everybody with me on the concept there? So here's what happens. The electrons shoot out of the electron gun. They hit the phosphor, causing it to glow. Then they bounce off inside. Well, remember that opposite polarities attract each other, which is why I went through that earlier this morning. If I'm a little old negatively charged electron, I'm going to find plus 20,000 volts rather attractive, don't you think? Opposite polarities attract each other. So once they've bounced off, they've lost all their energy. They no longer have any kinetic energy, but they still have a negative charge. It's an electron. It has a negative charge. But after it's bounced off, it doesn't have any energy, so what it does is it immediately attaches itself to the nearest outside wall, which is charged at plus 20,000 volts, where it gets sucked along the wall, the aquadag, and out the second anode, and into the high voltage unit, and eventually it'll get passed to ground, and that's how we get rid of those spent electrons. That's what the high voltage is there for. The high voltage at the second anode is there to remove those spent electrons so that they don't form a negatively charged cloud down here, preventing the electron beam from getting to the front of the screen. The second anode the voltage at the second anode is not there to attract the electrons toward the front of the screen, as you often mistakenly hear people explain it. You talk to a hotshot, most hotshots will answer this way. You say, oh, what's the second anode voltage for? And, oh, well, that attracts the electrons toward the front of the screen. It's a very logical explanation. It happens to be incorrect. That's the purpose of the electron gun. On the electron gun, there's a little gizmo here that I didn't mention to you. You may have noticed this thing hanging out off the end here. If you look real carefully at this thing, this is actually a twofold device. If you look real carefully, do you see that there's a residue inside there of some powder? This thing is referred to as the getter. You don't really have to know this part of it anyway. It's called the getter, G-E-T-T-E-R. When they first manufactured the picture tube, they suck as much of the oxygen out of the end as they possibly can. There's a glass nipple on the end here where they suck all the air out, but they can't get it all out. This electron gun sits here. This part of it is resting right against the glass of the picture tube. Once they've sucked all the oxygen out, they then use a coil to do something known as inductively coupling. Don't worry about it. They heat up that and cause it to burn up by putting a coil on the outside. It's like putting metal in a microwave oven. Same exact principle. It vibrates the atoms in there and they flash. This is flash powder like the old-fashioned photographers used to use in the Civil War. And what that does is it burns up the oxygen. It gets the oxygen out, hence the name getter. Well, you don't really care about that, but what you do care about is the fact that this also conducts the voltage from the second anode along the aquadag to this part of the electron gun right here, which happens to be referred to as the accelerator grid. This is connected to this outside ring, And that's what picks up the electrons for their final push to the front of the screen. It like picks them up and throws them out at the front of the screen like a baseball pitching machine, kind of. You know, the ball rolls toward the pitcher machine, and then the counter-rotating wheels kind of shove it toward the front of toward you. Well, that's what that's for. So that's what the second anode is for. The second anode and the high voltage is there at the high voltage at the second anode, I should say, is there to remove those spent electrons after they've struck the front of the screen, because if we didn't do that, we wouldn't see any image at all on the front of the screen. Everybody with me on that? Okay. Now, what this means is this. If for some reason you lose high voltage, you will see nothing at all on the front of the picture tube. If you lose high voltage, your symptom is this, a totally blank screen. But what this also means, and this is important, if you see any kind of normal brightness on the front of the screen, you must have high voltage. For you to see anything at all on the front of the screen, the high voltage has to be there, doesn't it? Otherwise, you won't see anything at all on the front of the screen. So that's a real important thing to know, that if you see anything at all, the high voltage is good. And since the high voltage comes from this thing called the flyback transformer, it means that the flyback transformer is good. We'll talk more about this later on. Now, many of you are aware that there is some high voltage that's stored somewhere in a monitor after you turn it off, and this is really where you're paranoid. You just don't know what can you touch and what can't you touch. Okay, well, first of all, you saw that the monitor's on now. It's on now, as you can see. All right, touching, not getting a shock, not getting a shock. I do this for effect. I don't do this normally because it's stupid. But what I'm saying to you is it's not going to leap out and get you. Okay? Now, certainly in a monitor, you don't want to touch anything with the power on. But if I turn this power off, here's the second anode here. It is true, or has been true in the past, that there is some high voltage that's stored somewhere in a monitor. And it's actually the picture tube itself that stores the charge. The picture tube acts like a capacitor and can store a charge. And in old-fashioned monitors, made before about 1990, this was true across the board. New monitors, modern monitors, however, are self-discharging. That is to say, after you've turned them off and let them sit for a while, there's a thing called a bleeder resistor that's here inside the high voltage unit that bleeds that charge off to ground. Maybe you don't even want to trust that, but it's true. And that's why I could grab the thing and not have to worry about getting a shock. Now, I am going to trick this monitor into being a non-self-discharging monitor for the sake of discussion here. I'm going to trick this monitor into being non-self-discharging. Kids, don't do this at home, because here's what I'm going to do. I am going to use the suction cup action to hold this in place. What will happen when I turn it on is I can get a charge to jump to the picture tube, but when I turn it off, it won't be able to jump back. And you know how when you turn on a monitor, sometimes you can hear that static, that sound? You know, that's what I'm going to listen for. Okay, I heard it come on. Let's see if the CRT is charged. And we should see just a little tiny spark. Oh, yeah, definitely. Okay, now what confuses people is that not knowing that modern monitors are self-discharging, they use a grounded clip lead to discharge the picture tube. Did I just do something terrible there? I got a feeling I just discharged a second anode right into the sync amplifier. I didn't have this end grounded. Oh, shoot. I guess we're going to find out later on. I think oh, Excalibur. Oh, all right, well, anyway, let's see what happens. What confuses people is that most people know how to discharge a picture tube. And to discharge a picture tube, all you need is a black clip lead and a screwdriver with an insulated handle. It's very important that the clip lead has to be black because you're going to ground this thing, and it'll only go to ground through a black clip lead, so that's really important. And what happens is, that was a joke, okay. What happens is people will ground the clip lead, and it's real easy to do. To discharge it, all you do is put the clip lead on ground and holding the screwdriver by the insulated handle, shove it under the second anode. I'll show you in just a second. But what happens is people don't realize it's self-discharging, so they never hear the spark. And now they're all like, is it discharged or not? I don't know. I'm not touching that thing. You touch it. I'm not doing it. Well, you don't really have to be worried about it. If you didn't get a spark, it's because it wasn't charged. So it's real simple. What I think is really hilarious is that I've seen a number of casinos where somehow they've managed to come up with a screwdriver that's a meter long like this, and they've wrapped a big wire on it and soldered it on there, and they're back there like D'Artagnan, trying to discharge the second anode like this. You don't really have to be that paranoid about it, not really. Let me put this, in fact, let me try something here, because there's a very interesting phenomenon here that you need to be aware of. In some monitors, and in the self-discharging monitors, this is not much of a problem. After you've discharged the CRT once and let it sit for a while, it mysteriously recovers some of the charge. It's a very interesting phenomenon. And I've heard people tell me all kinds of things like, the funniest explanation was, it gets the charge from the air. I thought that was really the cleverest of all. Well, it isn't getting the charge from anywhere. It happens to be a phenomenon. You don't have to know about it. It's called dielectric absorption. It's the inability of a capacitor to fully discharge, and we don't really have to worry about it. But let's see if just out of curiosity, you saw me discharge it. Let's see if we can get another little spark out of this thing. So I'm just going to connect the black clip lead to ground this time. Oh, man, I don't know what I did to it. We'll find out. I'm just going to connect it to the chassis. Now, you're not actually grounding it. You're not actually grounding it to the earth ground. What you're really doing is shorting the outside of the picture tube to the inside of the picture tube. So I have one clip lead, the clip lead here, one end of the clip lead, just on the metal frame, because remember, the outside CRT is grounded to the same place. And let's see if we get another little spark out of this thing. We might. We might not, so don't get your hopes up, but let's see. Focus. There we go. And you might hear it more than see it even. Just a little tiny one. I could hear it a little bit, but you didn't hear much of it. So it's nothing that you really have to be, super paranoid about. Go ahead and stick the thing back in. What I think is really fascinating is some people have not seemed to get the concept of holding the screwdriver by the insulated handle and shoving it underneath here. And what I've seen people try to do is this. Reach in here and peel it back to shove that underneath it. Well, of course, by the time you get here, you are the screwdriver, aren't you? Right? And of course, you never do this with the power on. With the power on, you'll draw a big old 3-inch arc, and you'll melt the end of the screwdriver, and you're likely to have to change your underwear, to be honest with you. So let's see if I blew it or not. That's just out of curiosity. Still comes on, so I heard the static come on, so I know that the high voltage is there, and I know the B plus is good, and there's some other stuff that I know is good as well. Uh-oh. Yeah, I think I blew it. I think I sure did. I get nothing now. Well, it's a good thing I have all lunch to repair it, huh? Or all of tonight, really. So that was a bad thing. What I did there is not anything I would have done in normal circumstances. It was an accident, obviously. I didn't see anything at all on the screen when I turned it on, and so I won't know until after I look at it. I'm a technician. I should be able to fix it. What the heck? All right. So anyway, so that's what the high voltage is there for. The high voltage is there to remove those spent electrons after they've struck the front of the screen. Does that make sense to everybody? Okay. And that's it. That's how a monitor works. All right, so turn to page 13 now, as I mentioned previously. And yesterday we went over the basic theory of operation of monitors. And as you can see, they're fairly straightforward. I mean, the way it works is really fascinating. I think it's really interesting how they work. We don't care so much how they work, though, as how they fail. So that's kind of where we're going to go for the next couple of days, is how things work and then how they fail. On page 13, you see that we can break the monitor down into 7 basic circuits or 7 basic sections. Let's take a look at the monitor sections, shall we? Section number 1 is the power supply. Now, as I mentioned before, I guess I didn't mention it to you. In a monitor, yes I did, the main power supply in a monitor is referred to as the B plus power supply. There are many power supplies in the monitor. That's what we're going to look at today, in fact. And we have lots of power supply failures, so we're going to take a lot of time on the power supply. It's real neat how it works, and there's some real straightforward failures, but we're going to kind of go through that today. There are many different power supplies in the monitor, but the main power supply, the big wazoo, the one that powers most of everything in the monitor, we refer to that as the B plus power supply. And as I mentioned previously, that voltage can vary. In some monitors, like Saronix, it's as low as 77 volts DC. I've seen it as high as 125, 126 volts DC. I think I've even seen one monitor where it was 136 DC, as I recall. But it's somewhere in that ballpark, somewhere in that range. It's called the B plus power supply, and again, we're going to look at that today. Section number 2. The video amplifiers. And remember, there are actually 3 video amplifiers in the monitor. Remember, there's the red amplifier, the green amplifier, and the blue amplifier. We're going to look at those in tremendous detail. You'll see how easy that is to understand and how to troubleshoot. That's a piece of cake. That's actually a lot of fun, too. Section number 3 is the blanking circuit. Remember that when the beam is at the far right-hand edge of the screen, we have to quickly make it fly back to the left-hand side, but we don't want to see the retrace lines during that time, so the blanking circuit activates. Remember to turn off the guns during the retrace time. Both the horizontal retrace, when the beam is at the right-hand side, it has to quickly come back to the left. And remember, when the beam is at the bottom of the screen, how it really has to zigzag its way back up to the top of the screen. We don't want to see those vertical retrace lines, remember? So the blanking circuit activates during that time period as well. Now, blanking and video are really closely related if you think about it. They both kind of do the same thing in a way, in that they're both really controlling the electron guns. The video amplifiers control how much each gun turns on. Remember, the higher the voltage, the brighter that color is. The blanking circuit only does one thing. It turns off all 3 guns simultaneously during the retrace times. But they do both control the electron guns. And so in that regard, in modern monitors, those 2 circuits can be combined into one integrated circuit, more or less, that's controlling both of those things, both blanking and video amplifier. And the reason I'm making a point of mentioning that is, and I kind of hinted this yesterday, you don't see very many blanking failures. Blanking failures are really, really rare. And in fact, we're actually, when we look at the monitor, we're really not going to discuss it. Because even if you didn't know that blanking existed, you would still be perfectly successful at fixing monitors, because it's just not a common failure at all. It just really isn't. Section number 4 is the sync circuits. And remember, there are 2 sync circuits. There is vertical sync that keeps the picture from rolling vertically, remember, and there is horizontal sync that keeps it from freaking out, doing that weird scrambly freaked out effect that it has. Section number 5, vertical deflection. Vertical deflection. And of course, that's responsible for filling the screen from the top to the bottom. Section number 6, horizontal deflection. And of course, that makes the beam move left and right across the face of the screen. And section number 7, last but definitely not least, the high voltage. And what I'm referring to here is the high voltage at the second anode of the CRT, as we saw yesterday. The high voltage, by the way, is sometimes referred to as the EHT. Sometimes you'll see it referred to as EHT. EHT stands for extremely high tension. Sometimes they refer to that as extremely high tension, or EHT. You know how, like the big power lines that travel across the country that are the high voltage lines, how sometimes we refer to those as high tension wires? That's really kind of the same term. Tension is actually another word for voltage. In a way, it's a more correct term. In other languages like French and stuff like that, it's like, we call it voltage, they call it tension or something like that. We say it's voltage measured in volts, they say it's tension measured in volts. So you'll often see this term EHT, extremely high tension. I always assumed that that was their state of mind while they were working on the high voltage, that they were extremely tense, but apparently it doesn't mean that at all. So there you go. Now, this is really important. If you're a little bit asleep, wake up. If you're a little bit asleep, wake up, wake up, wake up. This is a really important thing to know about monitors. In a monitor, there's a really close connection between the horizontal deflection circuit and the high voltage. And in fact, in almost every single monitor that you have out there, and there's some exceptions and I'll mention them later, the high voltage unit, the actual high voltage unit, also known as the flyback transformer, is actually driven by the horizontal deflection circuit. The horizontal deflection circuit drives the high voltage. The horizontal deflection circuit actually drives the high voltage. That's a really important thing to know, because it helps you troubleshoot. It explains all kinds of things about the kinds of failures that you have, which is what we're going to go over today. So anyway, here's the deal. When you have a problem with a monitor, once you know how the monitor works, and you can break the monitor down into these 7 sections, instead of agonizing over the problem and going, oh my God, what the heck can be causing the problem with my monitor? Instead, you kind of look at the way the monitor is put together, eliminate the things that cannot possibly be the cause of the problem, and anything that's left is something you have to test. So, for example, this monitor mysteriously developed a fault. Not the fault we saw yesterday. It's a whole totally different fault. Let's see if we can figure out quickly where the problem lies. Now, don't yell it out. As soon as this monitor warms up, everyone in this room, you'll all know exactly what's wrong with this monitor. So don't yell it out. I want to kind of show you what the philosophy of what I'm talking about here, the philosophy of this repair. Okay, so there's the failure. And depending on what was showing on the monitor at the time on the game, and I can't really simulate it too easily here, you might be seeing different colors appear in this. That's kind of a shame that it doesn't actually show that. Let's see if I can get it to just display it a little better here. Because this monitor has an additional problem, as we know, but we're not going to talk about that. Anyway, so that's the problem. This is the basic problem that we're looking at right here. Okay, so let's see what this might be, and let's see what it might not be. Could this possibly be a high voltage problem? No way. Why? Because you have a line, because you see something on the screen. Remember, if you lose high voltage, you won't have the electrons whacking against the front of the screen, and you won't see any brightness at all. So it's definitely not a high voltage problem. Is this a horizontal deflection problem? No way. Well, Frank says it's not because it's going all the way across, but we know that it's not a horizontal deflection problem for another reason. What is that? We have high voltage, right? Since the horizontal drives the high voltage, as soon as you eliminate high voltage as the problem, you've eliminated horizontal deflection at the same time, haven't you? But in addition, as Frank says, we do see a horizontal line on the screen, so I guess we have horizontal deflection because that's what the horizontal deflection circuit does, is makes the beam move left and right. So it's definitely not that. Well, if the horizontal deflection circuit is working, what do we know about the power supply? That's got to be there, doesn't it? I mean, it drives the horizontal deflection circuit. It drives everything, basically. So that must exist. Now, in the game, you would see this flashing red, green, and blue, depending on what came on the screen at the time. Like you can kind of see some colors in there, kind of, sort of. If you see it, can you see how there's some colors, some green and some blue in there? Let's pretend you do. Okay, so So we see colors, so what does that tell us about the video amplifier? That's got to be working okay. Okay. However, this screen is completely blank up here on the top, and it's blank down here on the bottom, so it must be a blanking problem, right? Nah! Blanking, we remember the zigzaggy vertical retrace lines. That was your big clue. And remember I mentioned to you also that they would be white because blanking controls all three guns at the same time. And we don't have anything that looks like that at all, so it's not a blanking problem. Is the picture rolling vertically? Is it doing that jagged diagonal stair-step thing that would indicate bad sync? Does it have bad sync?
Well, we really don't know yet.
Shh. No, it isn't. I mean, when you had a sync problem, you had a full screen, didn't you? Right? But it had that weird jaggedness, or it was rolling vertically, right? So it's not a sync problem. And of course, by process of elimination, this is a vertical deflection problem. Obviously, clearly, this is total loss of vertical deflection. There ain't none, no vertical deflection, total catastrophic loss of vertical deflection. Well, once I've gotten to this point, I know that it's not any of these other things. By process of elimination, I have eliminated 6 out of the 7 sections, haven't I? I'm not going to look at those sections. I don't care anything about those sections. Whatever my problem is, it ain't there. And this is kind of the thing that I see where some technicians kind of waste their time. I know lots of qualified technicians that are okay at fixing monitors. They do fix monitors. But they waste time checking things that can't possibly be the cause of the problem. In other words, if my problem is loss of vertical deflection, I don't want to waste time checking the B+ power supply. It's got to be there. But I see people doing that. It's like, hey, look, you know what? If you get up in the morning and your car doesn't start, you don't check the windshield wiper fluid, do you? And that's what this is. That's what I see people doing. So they eventually fix stuff, but it takes them a while to do it. As far as I'm concerned, my definition of what my job as a technician is to get to something that's broke, fix it, and get my sorry butt out of there as fast as possible. That's really my job. It's not really a matter of how clever I am or how I managed to find the one part that was bad and I never changed any parts that weren't the problem, or how smart I am because I got right to this problem. It's a matter of how fast I can get in and out and get the thing working. So as we'll see today, sometimes it might be a matter of narrowing the problem down to a certain circuit and saying to yourself, man, it's got to be one of them parts that are in that circuit, and maybe there's only 12 parts in that circuit, and maybe you can test 10 of them to see if they're good or bad, and anything you can't test, you just throw in a new part and see if the problem goes away. I am a parts changer. I got to tell you, and I totally admit it. I change parts like crazy. You know, if I even possibly think that the part might be bad, I just put in a new part. One of the things that enables me to do that is I have a mess of spare parts. Normally when I travel, I have this big suitcase, and it's completely full of spare parts. I have $300 or $400 worth of capacitors, and I have, probably $500 worth of probably less than that, maybe $200 worth of semiconductors, diodes, transistors, integrated circuits, and stuff like that. If I have the part right in front of me, and I think the problem might be related to that part, and I'm really good at soldering, which is a really important skill to have, I can just throw in a new part and see if the problem goes away. The parts are cheap. It's your time that's the most important commodity. So that's kind of my basic philosophy. Now, the hotshot engineer guys will really look down their nose at that. The really skilled technicians that use oscilloscopes and have this great skill, they'll say to me or to anybody that uses this technique, you're not a real technician, you're just shotgunning the circuit. To shotgun a circuit means to say to yourself, look, there's 6 parts in that circuit, why don't I take all 6 out, put 6 new ones in, I'm guaranteed it'll work. Doesn't that make sense? So that's called shotgunning, and the real qualified technicians will go, hot. But you know what? By the time that hotshot technician is done probing around with his oscilloscope and armed with an exact knowledge of how the circuit works and what might possibly have failed to cause the readings that he gets on the oscilloscope to be different than what's normal, and by the time he's narrowed it down to that part and changed the one part he thinks is bad, I've tested or replaced 6 parts with my meter and a soldering iron, and I'm home drinking beer while this guy's still doing this. And that's, of course, the most important thing in our lives. So, so there you go. I mean, that's just my philosophy, but it has really served me really, really well. I do know what I'm doing now. I don't mean to sound egotistical. I'm a pretty good technician. I know a lot of stuff now. You kind of have to when you teach it. You better know what you're doing. But I didn't in the beginning. When I first started repairing stuff when I was in high school, well, for example, I had a job fixing stereos. It's a stereo amplifier. There's a left channel and a right channel, just like there's red, green, blue here. There's a left channel and a right channel. The right channel is out, the left channel is working. All I did was compare one channel to the other, and where I found something different, I changed that part, and the problem went away. Nobody knew that I didn't know anything, but I didn't. Yes, sir?
In your experience, how many new parts have you found are bad, though? Because that's what those guys will say. You can put in a brand new part that's bad.
Yeah, the question is, in my experience, how many bad parts, new parts have I found? I do always test parts before I put them in. I just do. I always throw a meter on them, and I have found bad new parts, but it's extremely rare. It's extremely, extremely rare. I mean, it's a tiny fraction of 1%. I would say maybe one out of, this is a guess, I have no idea, maybe 1 out of 5,000, maybe 1 out of 10,000. It is a consideration when you stick a new part in there and it doesn't fix it, and you go, is the part I just put in there good or bad? And, I don't know. It's something to keep in the back of your mind, but I would say it's not anything to be overly concerned about. I do test them before I put them in. Now, the flip side of that is parts that test perfectly good that are bad. And at the risk of jumping out of sequence just a little bit here, I was in Atlanta a couple of weeks ago teaching a monitor class, and we had a problem where we were missing a color. We're going to talk about that next. I whipped out my meter. This is a real problem. I checked this transistor. It checked perfectly good. But something inside me, my intuition as a technician or whatever, said, I have the transistor anyway. Why don't we just throw it in? And I threw the transistor in, and it worked perfectly okay after that. That's why I'm saying I'm a parts changer. If I think that the part might have something to do with my problem, I will throw a new part in there. The parts are really cheap. The worst thing that can happen, though, is when you don't have the parts. You think it's a part, you order the part, you wait 2 weeks or 4 days or whatever for it to come in, you stick that part in and it doesn't fix it. I mean, that's very frustrating. Having a good collection of spare parts is a really important thing to do. In the past, we've run an article in Slot Tech magazine about Saronic spares. And in fact, they actually made up a kit. For those of you that are doing Saronics repair, which is pretty much everybody, if you call up Saronics and ask for the Randy Fromm kit, they have a $300 kit of parts. That's all the parts you need to fix all the Saronics monitors. Everything from the little relays to the transistors to the, they call them the PRAs, the precision resistor arrays, everything. You just call up the parts and say, hey, Randy said you got that kit. It's $300. They actually have a kit. And in future articles, you'll be seeing things on what capacitors to have in stock and stuff like that. But having the spare parts is really great, and you'll see how this works as we go through this thing. So anyway, getting back to this, so that's total loss of vertical deflection. So the point I'm making here is now we've eliminated 6 out of those 7 sections. I know it's a vertical deflection problem. Well, of course, we're going to look at the vertical deflection circuit in great detail. That'll actually be tomorrow. But at this point, what I will do, as you'll see tomorrow, is I will make one quick voltage measurement. Maybe 2, but probably just 1. And based on that, I will either replace an integrated circuit or somehow fix my power supply so that it's getting power to the thing, and I'll fix that circuit. And you'll see how this goes tomorrow. But I'm not going to waste any time checking all this other stuff, because whatever that my problem is, that isn't my problem. Okay. Yeah, hang on just 1 second. I have to be careful about this because in my pattern generator, when the battery starts to fail, it does this. So I just want to make sure that the thing we're looking at is what I think we're looking at. Stand by just 1 sec. Okay, well, I'm glad I did that. Okay, well, let's say we have a problem like this. Okay, you might have a problem that looks like this. Hey, shut up, Frank. Oops. Sorry, I didn't mean that was rude. I'm sorry, Frank. I was really just kidding. Or you might have a problem that looks like, sorry. Gosh darn it, stay there. Oops, that's two problems at once, isn't it? Well, let's just leave it at this. Well, okay, then let's use this as the problem for now then. We'll do this one first. There, how's that? Okay. So you might have a problem that looks like this. We went through this one before, though. This is obviously not a difficult problem to figure out. So again, let's say you didn't know about the monitor, and you look at this thing and you go, well, gee whiz, what could it possibly be? It's obviously not a power supply problem. It's obviously not a video problem. We can see all three colors, red, green, and blue in there. We don't see the retrace line, so it's not a blanking problem. The high voltage is there, obviously. The horizontal deflection's there. It's completely filled out in the vertical direction. Clearly, this is a sync problem. Is this a horizontal sync problem or a vertical sync problem? Horizontal sync, right? And we'll look at this when we look at the schematic diagram later on, which we will do. We'll look and see what I did. If you recall yesterday, I took the second anode voltage, and when I discharged it right into the sync amplifier accidentally. I disconnected the wrong end of my clip lead. And so this is bad horizontal sync. So again, once you know that it's a sync problem, you eliminate all this other stuff, you would just look at the sync circuit. Now that having been said, if we can disregard the sync problem and look at this problem, all right, everybody with me on that? So I'm sorry that sync problem exists. There's just nothing I can do about it, unless maybe I'm lucky and I can turn this off and back on again and have it synchronized. Not really. I can slightly adjust the horizontal hold control. Unfortunately, they put the horizontal hold control, that would have straightened it out. They put the horizontal hold control so far down in there that you'd kill yourself getting it out. You actually, to adjust it, you would actually have to pull the chassis out to do it. So anyway, so that having been said, in this case, when we look at the sections, obviously, we have high voltage in this case. Obviously, horizontal deflection's good, vertical deflection's good, sync's good, blanking's good, power supply is good. I see blue on the screen, so the blue is okay. I see green on the screen, so the green's okay. We're missing red. And what's interesting about this is that I see this kind of a problem all the time in the field, not only in casinos, but in airport monitors and all over the place where, you're looking at the picture and it's there. It just looks weird. And I've had people look at this problem and go, I've been trying to adjust that monitor for a week and I can't quite get it working right and I can't figure out what's wrong. But of course, all you see is green and blue and cyan, right? Because you can make cyan out of green and blue, and that's all that we're left with there. So in this case, we're missing red. So in this case, not only have we eliminated 6 out of the 7 sections, we've eliminated 2/3 of the remaining section. Everybody with me on the concept there? So, that's the kind of thing that I'm talking about when we're talking about, telling which of the sections is bad. Now, pardon me, Frank? No, that's not why it's cyan. It has to be cyan. There's no red. So absolutely. There's one other thing that could happen here. In this case, we have no red. It's either that something's wrong with the red in the monitor or somebody dumped a bottle of Izine on the monitor and got the red out. All righty. So, everybody with me on the philosophy there is all I'm really interested in. So, that having been said then, let's take a look at, let's start with the video circuit, because the video circuit is interesting and fun to look at. Let me see where that is. I suppose I should have put an index in this thing. Sorry? 22. You'd think I'd know my own book, huh? You're such a guy. He's right, 22. Okay. Yes, sir.
I got a color question.
Yes, sir.
We always say a color is blasting when you only have one color, but is that just too mixed? Or is there another?
Oh, that's right where we're going. Right, that's what I'm covering right now. Good question. And that would be an apropos description. I've never heard that before, but we'll do that right now. Okay. Now, remember the way this thing works is that we have the CPU, the logic board, whatever you want to call it, and it sends out the red, green, and blue signals to the monitor. Here's the monitor. Here's the CRT. The three cathodes, which are actually the things that are being controlled in the electron gun, it's really the cathodes that we turn on and off, as you'll see. We have the three video amplifiers. And like that. When you get to a monitor, if for some reason you were missing a color, as we are here, your first question has to be, is it really a monitor problem? Which, of course, in the casino industry is real easy because you have the advantage of Swaptronics, as you know. And so in the casino industry, it's easy. You pop out the monitor. Well, first you pull it out and push it back in just to see if it's a connector problem, don't you? And that's it quite a bit of the time. But, you pull the monitor out, stick in another monitor. If the new monitor works, obviously the problem isn't here. The problem is in the monitor. So for you guys, that's a real easy way to tell. My background's actually from the amusement industry, and in the amusement industry, video games, coin-operated video games, we didn't have that option. So we actually would have to either have a pattern generator like this one, or somehow determine that we do have the voltage at these wires to see if we had an input to the video amplifiers. But in this case, we know that it has to be in the monitor. It just has to be. The next thing we want to do then is start working on the monitor. And the first thing that I want to show you is a video circuit that you do not have. You don't have, this is an old video circuit, but I want you to see this so you get an idea of kind of what I'm talking about here. On page 22, if we take a look at this schematic diagram, if you look right up here on the top, you see where it says red, green, blue right up here on the top, and you can follow along on the monitor if you want. That's where the red, green, and blue signals come in from the computer board. So just kind of casually follow me down here. Follow the red wire down as far as it'll go and hang a right, and you see a circuit that is made of two transistors here. They're labeled X101 and X102. I just want you to see that they exist. If you've never seen a transistor before, that's a transistor. X101, X102. Now, go back up to where the green wire comes in on the top and follow that wire down, 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 down as far as it'll go. Hang a right, and you see two transistors there, X104 and 105. Again, I just want you to see that they exist. That's all. Now, go back up to the blue, follow that wire down, 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 down as far as it will go, and go to the right, and you see two transistors, X107 and X108. And what I want you to see here is it's pretty obvious that we have three identical circuits there, isn't it? I mean, even if you don't know anything about electronics, if you're just looking at this as a bunch of squiggles and lines, clearly we have three identical things there. So that being the case, let's just look at one. Let's just look at the red input. So again, go back up to the red input, follow it down, and to the right. At this point, we're at a junction of a resistor and a capacitor, and that video signal comes in up through the resistor to this lead of the transistor, which is called the base. You know, here again, we've already gone through transistor theory in my normal class. For those of you that don't know transistors, this lead right here is referred to as the base. The lead on the top is the collector, and the lead on the bottom is the emitter. Let me take just 1 second to explain that on the board. Hang on a second. Real quick look at transistor theory, but really quick. And if this confuses you, it shouldn't, because it's real simple. This is not complete transistor theory by any means. This is the schematic symbol for a transistor. Typically, they draw a circle around it like this. A transistor has 3 leads. And the leads have names. It's kind of important to know the names. The lead over here with the arrow on it is referred to as the emitter, E-M-I-T-T-E-R, the emitter. And as the name implies, the emitter emits something, and what it emits is electrons. Here, let me just draw that even bigger. Emitter. On the same side as the emitter, this lead on the top here without the arrow on it, we refer to that as the collector. It's called the emitter and collector. It's called the emitter because it emits electrons. It's called the collector because it collects electrons. Not that you care. You don't. You just care what they're called. And over here on the left-hand side, this lead is referred to as the base of the transistor. So it has 3 leads, collector, emitter, and base. And all a transistor is a switch. That's really all a transistor is. In a transistor, the main switchy part of the transistor is between the collector and the emitter. When the transistor is turned off, there is no connection between the collector and emitter. When the transistor is turned on, the collector and the emitter are connected together. That's really all there is to it. When the transistor is off, there is no connection between those two. When the transistor is on, they are connected together. What turns the transistor on? Well, that's what the base does. The base is the controlling element of the transistor. All we have to do is put a little bit of juice on the base, and the transistor turns on. And it doesn't take very much. It really only takes 7/10 of a volt. Well, remember, I mentioned that to you yesterday. What's the voltage that it takes to turn on the gun in the monitor? 7/10 of a volt is what turns it on all the way, doesn't it? So, hey, that kind of makes sense. 7/10 of a volt turns on a transistor. 7/10 of a volt is what comes out of the computer or the pattern generator, so it all kind of works together. And it also makes sense that the input comes into the base, right? We looked at the input here. The input comes into the base of the transistor right there, so that kind of makes sense. And you'll see that that's true, all over the place. I mean, that's really how it's done. So, I mean, in a nutshell, that's all there is to a transistor. The easiest kind of way to kind of think of a transistor is imagine a regular toggle switch, like a wall switch, that has a couple of screws on the side and has the toggle. These screws are like the collector and the emitter, and the toggle's like the base. When the toggle's down here in the United States, those 2 screws are not connected together, just like when the transistor is off, the collector and emitter are not connected together. When I flip the toggle up, it shorts those 2 screws together, doesn't it? Same thing. When I put 7/10 of a volt on the base of the transistor, the collector and the emitter are connected together. So, I mean, in a nutshell, that's really how transistors actually work. Let's go back to the schematic diagram and see how the rest of the circuit works. So, let's start over again. You come up here to where the red comes in. You follow the red wire down and to the right, and it goes up through that resistor into the base of X102. So that makes a lot of sense. The output happens to come off the lead on the top, the collector. And if we follow that to the right, it goes through a resistor R109, as you can see, and down. And it goes into the base of a second transistor here, X102. For those of you that are hip to electronics, you may notice that X101 is NPN, where X102 happens to be PNP. Kind of hard to tell, but that's the emitter arrow on the top there. And if it points in toward the center of the symbol, it's a different polarity, PNP versus NPN, which is this one. If that didn't make any sense to you, don't sweat it. So the output now comes off of the collector, the emitter, the lead on the top here, and follow that wire over to the right, and it goes to what we refer to as the neck board of the monitor. This is a separate printed circuit board. It's the neck board of the monitor that sits on the neck of the monitor. Well, the neck board, here's neck board, which we're going to look at in great detail coming up, the thing that hooks up to the CRT socket, commonly referred to as the neck board. They have a somewhat more sophisticated name for it here. They call it the CRT socket printed circuit board assembly, neck board. Anyway, so if we go back to 102 here and follow the output from 102, comes off the emitter on the top, it actually leaves the main printed circuit board. This heavy dashed line that you see around the majority of the circuitry here is the main printed circuit board, the main chassis. You know, that chassis there. And then we have the neck board. So the output comes off the emitter and goes up into, as you can see, X103 on the neck board. And that, if you follow the collector, the lead on the top, out to the right, to the right, to the right, it goes through a resistor, and you see the little backward L-shaped thing that is the cathode. Everybody with me on that? So my question to you then is, how many transistors are there in total for each color? There are just 3 for each color. Well, how difficult could it possibly be to determine what's wrong with the color amplifier? First of all, there are only 3 transistors, and you should know how to test transistors. You could just replace them if you had to. But if you had a green problem, and the problem was in the monitor somewhere, on the electronics in the monitor, all you'd have to do is check those 3 transistors and replace any that are bad. Now, I would always start out with the output transistor, the transistor that's on the neck board itself, that's connected right to the cathode. Those are the video output transistors. The video output transistors are the hardest working transistors in the monitor. And they're on the neck board, and they're always the 3 largest transistors on the neck board. So on this neck board, it's these 3 that are mounted on these heat sinks, as they're called. These finned aluminum things are known as heat sinks, and they're used to help keep the transistor running cool. That's extremely important. Also in this case, you'll notice, for those of you that are unfamiliar with this, you'll notice some white goop here that looks like it leaked out of the transistor. It didn't leak out of the transistor. It's put there intentionally. It's something known as heat sink compound. Heat sink compound. It's used to fill in any tiny microscopic gaps between the transistor and the heat sink so that it conducts the heat away from the transistor. It doesn't conduct electricity, of course. It just conducts the heat away. When you replace transistors, you're supposed to put a little dab of heat sink compound on them. I don't always do it. You're supposed to. But anyway, there are 3 video output transistors, 1 for each color. And so there's 1 here, and there's 1 here, and there's another one right behind this piece of styrofoam. Right there. And we could look at all kinds of neck boards, and you'd see the same thing. Here's a different neck board, different monitor, but here you see the 3 video output transistors mounted on heat sinks, or actually heat sinks mounted on them. There's 1 here, there's 1 there, and there's 1 there. So anytime you're looking at things in 3s, here's another thing that's in 3s, 3 big resistors. Anytime you're looking at 3s in the monitor, you're looking at color, you're looking at RGB. Well, in any case, I would start with the video output transistors. I would start with the video output transistors because they work the hardest. And remember I said that things that work the hardest are the things that fail the most. Since these are the guys that are driving the cathodes of the electron gun directly, it's very, very likely that these are the transistors that this would be the transistor that was bad. And it'll be bad if you're missing a color, but it would also be bad if you have too much of a color, which is what you refer to as blasting. Let me see if I can simulate this for you here. This will either completely destroy this monitor or it'll show me what I want to show you. But it's not, like I said, it's not my monitor, so I don't really care. I'm going to magically fix the red problem. Ooh, see there? All right. And I'm going to show you what I'm going to do in just a second. Let's see what this does. Bright red, right? Incredibly bright blue. Do you see retrace lines as well? Okay, but they're... Okay. And green. Okay, so that's what you refer to as blasting, right? Well, in that case, do not look at a problem like this and say, wow, I'm missing red and blue. The red and blue are there. The problem is that the green is just so overpowering that you can't see the red and the blue. Think about it. We have 3 identical circuits. Unless you have a crack in the neck board or you've had some kind of catastrophic failure like a shorted electron gun in the CRT, the chances of 2 circuits failing simultaneously are not very good compared to 1 being bad. So in that case, we have too much of a color, and that's a really important trick, actually, that I'm going to mention to you in just a minute, in just a second. So anyway, but the point that I'm making here is this. Referring to the schematic, if I had a red problem, in this particular schematic, it's X101, X102, and X103. It has to be one of those 3 transistors that are bad. Not only that, though, there's other easy ways that you can troubleshoot this thing as well. For example, is not X101 the same as X104, the same as X107? I mean, aren't those 3 the same transistors in the same circuit? Of course they are. Is not X102 the exact same thing as X105 as X108? Of course they are. You can swap transistors. In other words, if I have a red problem and I take 102 out and I take 105 out and I swap their positions and now I have red but I don't have any green, duh, I guess that transistor that I just put in X105 must be bad. I do this all the time. I'm not afraid to admit it. I'm absolutely not afraid to admit it. You might say, well, wait a minute, you're supposed to be a good technician. How come you can't just check the transistor and if it's bad, stick in a new transistor? I could. Except that I try to do things 100% accurately if I possibly can. When you test, this is real important, when you test a transistor with like a meter, it is entirely possible that the meter can lie to you. When you use a digital multimeter to test a transistor, you're only checking it at about 1.5 volts, 2 volts, depends on the meter. And it might check good. If I take that same transistor and put it in the circuit, it could fail at 100 volts or 200 volts or whatever the voltage happens to be. If I swap the transistors, I know for sure, don't I? It's absolutely 100%. That's why soldering is so important. If you don't know how to solder, and by soldering I mean component removal and replacement is really what I'm talking about, you need to get a junk monitor chassis or something from your shop and take all the parts off and put them all back on and do it again and again and again. It takes a lot of practice to be good at soldering, but it's the most critically important thing you can do. The class we did at Chip-In's Island Resort, we had a couple of situations where the people found the bad part, they stuck in a new part, but they messed up the soldering, and they either A, caused more problems, or B, it just didn't work. Where a quick and accurate solder job, and they would have been done in 15 minutes. So you create your own problems with poor soldering techniques. So anyway, so you can swap parts, and I do that. I'm totally not afraid to admit it. I just do it. And in fact, like I mentioned before, I'll even replace a part. If it tests good, I'll just throw a new one in just to see if the problem goes away. There is another little trick for checking the transistors. We have 3 identical circuits, so you can comparison test one to the other. For those of you that know how to check transistors, you know that it's kind of a 6-step process. With your meter set on diode check, you check it between base and emitter and base and collector, and then you reverse the leads and do the same check, and then check between collector and emitter. This is what that first article is in the book, if what I just said didn't make sense to you. Well, you can do that with these things. In other words, in circuit with the power turned off, we can check these transistors. As many of you are aware, when you check transistors in circuit, very often they don't check good in circuit because of all the other parts that are connected to it that affect the reading. However, we don't care in this case because X101 is the same as X104 is the same as X107. So if X101 checks weird in circuit, but it checks the exact same weirdness as 104, then that's normal, isn't it? I don't care why it's checking weird. I just know that that's normal. On the other hand, if I check 102 and it checks weird in circuit, I check 105 and it checks differently. I'm still talking about missing red here, by the way. I check 102 and it checks weird. I check 105 and it checks different from 102, but 105 and 108 check the same as each other, and both of those channels are working, aren't they? Then I got to know that 102 is the problem, or something hooked up to it is, one or the other. Now, when you do this, do yourself a favor. Don't do the stupid thing that I did for years and years and years. For years and years and years, I did the stupidest thing. When you check transistors, you're looking for something called a junction drop, and typically on your meter, it's a reading of about 0.5, 0.6, something like that. And again, if you don't understand that, read that article. So what I was doing is writing down on a piece of paper, okay, X102, base to emitter, 0.5. Base to collector, 0.47. Now reverse the leads. Base to emitter, 1.2. You know, I was writing down all 6 readings. What a stupid dork. All you have to do is go base to emitter on 102, let's say, base to emitter 105, base to emitter on 108. You get it? That way you're only looking at the same number each time. Then base to collector, base to collector, base to collector, collector to emitter, collector to emitter, collector to emitter. You get it? Because then you don't have to remember the number except for just like a fraction of a second, and away you go. So that's really the way to do that kind of comparison testing. Does that make sense to everybody? I mean, except for those that don't know how to check transistors, of course. And I'm sorry, I don't mean to keep pointing over here. I'm just kind of gesturing. I didn't mean to say anything by that at all. Okay, now, we don't use all transistors anymore. If you turn to page 24, let's take a look at this monitor, or something real similar to it anyway. Two things have happened in the evolution of monitors. One is that instead of using all transistors, we now have an integrated circuit video amplifier. And you see it here, it's IC501. It's this LM1203. If we look at this schematic, the input comes in on the left, and you can see where it says red, green, and blue. That's where the inputs come in. And if we follow that red wire, instead of going to a transistor, it goes through a capacitor there, and it goes into pin 4 of this integrated circuit of type LM1203, which happens to be this guy right here. This is a real common integrated circuit. This integrated circuit is in the majority of everyone's computer monitors on everyone's desks all around the world. It's extremely common. I could go into any office building and cannibalize their monitors probably and come up with that chip. There have been some new ones since this design came out, but they all kind of work the same way. We're going to talk more about this in just a second. This is the video amplifier integrated circuit. So all those other transistors are actually in that integrated circuit, those first 2 transistors that I showed you for each color. The way it works is that whatever comes in one side comes out the other. So in other words, red comes in pin 4 here, and it comes out pin 25, it looks like. Yeah, pin 25. If we look at the the green input, it comes in, goes through a capacitor, and goes to pin 6, it looks like. It would come out pin 23, well, I don't know which pin it comes out, actually. Pin, that one. 20, pin 20. And you look at the blue input, comes into whatever pin that is, pin 9, and it comes out whatever pin that is, 14, 16? 16. Anyway, so that thing is the amplifier. Now, if we follow that out, let's just look at the red, go up here to pin 25, come out, goes through just a 100 ohm resistor and goes to the base of Q502. That is the video output transistor. How do I know it's the video output transistor? Well, the first time I looked at the schematic, I didn't. I looked at the schematic for the first time and I went, what? I don't know what this is. Let's follow it out. Let's follow the collector. And if I follow the collector lead up to the right, it goes through just a 100 ohm resistor. Look where it goes. It goes to the cathode, that backward L-shaped thingy that is the cathode. So that must be the video output transistor, that guy right there. And when we look at the actual neck board of the monitor here, And this is a slightly different monitor. Not terribly different, but slightly different monitor. There's the video output transistor right there, mounted on the heatsink. In this case, the integrated circuit's not a 1203. It's a different one. It's a somewhat smaller one. It works exactly the same way. It's just a slightly different integrated circuit. And that goes to the output transistor. So, the input comes into the integrated circuit, comes out of the integrated circuit, goes right to the video output transistor, and right to the cathode. Gee whiz, what could be simpler? Wait a minute. If that's the case, if the input comes into the amplifier and right out to the output transistor, what the heck are these things? Check this out. There's like 3 identical circuits here, made of a couple of transistors each. And those circuits are similar to, but not exactly the same as, these little circuits right here that are mounted on this little board right here. See a couple of transistors? It's not exactly the same circuit. We're going to look at this one later on. The input actually comes in here through this connector. This connector comes right from the Metromate drawer connector. This is an amp Metromate drawer connector, as it's called. This is not a bow plug, as some people have mistakenly referred to that as, BEAU. That's a completely different kind of connector. But anyway, it comes right from there to there, and it goes from there to these little transistors, and from there it goes right to the output transistor. Well, what the heck are those things? Well, the first time I looked at this, I had no idea. I mean, I said to myself, well, gee whiz, I know how video amplifiers work. The video comes into the amplifier chip, and it comes to an output transistor, which I've replaced 1,000,000 times, and it goes right to the cathode. So what the hell are those things? Well, when I first looked at it, I hadn't a clue. I do realize now that they have something to do with what's known as the auto bias. I mentioned that before to you, where these monitors are self-adjusting. That is to say, they automatically keep what's called the beam current, the color, at exactly the correct level all the time. And so that's what they do. But even if you didn't know that, and before I realized it, I didn't know that, we could still fix that because, first of all, you do see that there are 3 identical things. Well, if you had a red problem, I mean, that's obviously the red transistor, isn't it? Because we followed it right in from the red, and it comes right out. So that's the red transistor here. If I had a red problem and it wasn't that transistor, wouldn't you check these to see if these were good or bad? I mean, it says red bias right on it. Bias means putting a voltage on something. It's called biasing it in electronics. This one's clearly labeled red bias. This one's clearly labeled green. This one's clearly labeled blue. Golly gee whiz, if you had a red, green, or blue problem in this monitor, wouldn't you check those parts? Are you with me on the concept there? I mean, I'm not losing anybody, am I? So you don't even know how that circuit works. Do you have to know how the circuit works? Absolutely not. I have no idea how that circuit actually works. If you were to ask me to explain specifically, well, when this voltage does this, this transistor turns on and it does that, I absolutely wouldn't be able to tell you. I suppose if I wanted to waste my time, well, spend my time figuring it out, I could, or I could call the engineer or ask, or I could read in the book here, there's an explanation of how the circuit works, but I don't care. Look, I'm too busy. I got a red problem, I'm checking any transistor that has to do with the red circuit. Or I'm taking the transistors out of the red and moving them with green and seeing if the problem moves. Are you with me on the concept there? That's all I'm saying. That is why knowing how to test the parts or having a bunch of spare parts is really important. But if I have a red problem, that's all I'm checking is that on the neck board. I'm not checking the B+, I'm not checking the vertical. In other words, I'm going right to where the problem is and fixing it quickly and getting my butt out of there. Yeah?
Why are you just worrying about the amps and the transistors? You got capacitors that can dry out there?
Oh, we're getting there. I'm getting there. The question is, why am I just talking about the transistors? And I haven't talked about capacitors or anything else. Number one, transistors in the video amplifier, the transistors, the semiconductors, are way more likely to be your problem than anything else. I mean, they're 100 times more likely than anything else. Yes, there is a capacitor. There's that input capacitor that we saw, and yes, it's possible that that's going to be bad. When we get into the vertical circuit specifically, I'm going to really talk about capacitors and capacitor failure, and I'll bring it all full circle. I mean, it's a great question. He's saying, how come you're not talking about the other parts? Resistors are very unlikely to fail in this circuit. They're just extremely unlikely to fail. I've never seen a resistor fail in the video circuit. Never, ever, 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 ever. But output transistors fail all the time. And in this class that I mentioned to you in Atlanta, that's what it was. The video output transistor was bad. We had no color, and that's what it was. A bad video output transistor can cause you to have no color, or it can cause what you refer to as the blasting color, the too much red, too much green, or too much blue. It can cause either of those problems. So I always start at the output and almost always start at the output and work my way back, in the video circuit especially. Make sense? Okay, let's take 10. It's all good. A few more things about video. Number one, we just looked at this video circuit that looks like this, that has the LM1203 video amplifier integrated circuit. Inside this LM1203 is the 3 amplifiers that we kind of looked at with the first schematic, the one made of transistors. That's what's inside this amplifier. So there are 3 identical amplifiers. As you recall from yesterday, we use a triangle as a symbol for an amplifier. I want to mention to you something that is an easy assumption to make, but will be totally incorrect. Let's say that we had a problem where we were missing a color, like we're missing the color red. Do not say to yourself, well, I'm only missing one color. It cannot be the amplifier chip because, gee whiz, that controls all 3 colors. If the chip were bad, wouldn't all 3 colors be bad? That is an easy assumption to make. It seems kind of logical. It's totally incorrect. In this integrated circuit, there are 3 identical but completely separate amplifiers. Yes, they all live on one tiny little chip of silicon inside there, but they are actually 3 completely separate islands, if you will, living within this silicon chip. It is entirely possible for the red amplifier to be bad, but the green and blue amplifier to be good. So don't assume that just because you're missing one color, it's not the chip. That having been said, however, it has been my personal experience that the video amplifier ICs themselves are pretty darn reliable. I have actually never changed the video amplifier integrated circuit in a monitor. I've replaced plenty of output parts, but I've never actually replaced this. I'm not saying that doesn't ever go bad. I had one guy call me that said that he had just a bright white screen, uncontrollably bright, with vertical retrace lines on it, and he couldn't control the brightness. And we guessed that since all 3 amplifiers seemed to be totally turned on, causing white, of course, that the chip was bad. He replaced the chip, and that was the problem. But I personally haven't seen it. It doesn't work very hard, so it's not a very likely failure. The thing that works hard is the 3 video output transistors that are mounted on the heat sinks typically. They're not always mounted on heat sinks. In a small 13-inch monitor, it wouldn't be. But the larger monitors, they are. Those are the things that fail the most. Everybody with me on that? That's a real important thing. Number 2, when you have a problem where you're missing a color, before you start ripping into the electronics, trying to check the transistors to see what's going on there, you have to ask yourself, is it really the electronics, the chassis itself that's bad, or is maybe, let's say, the red gun bad? In other words, we're missing the color red. Question, is the red coming in from the game? Is the red video amplifier bad? And I'm not just talking about the integrated circuit, but those other bias transistors and the other things that are in that amplifier circuit. Is the output transistor bad, or is the red gun in the picture tube itself bad? That's entirely possible. The guns go out all the time. The older the monitor is, the more likely you are to have a gun failure. I mean, it's just super common. Well, we can figure out if the source is there, if we're getting the red input, because we've swapped monitors. So we know if we have the input or not. So that's not really an issue for us. But we do want to determine where the problem is here. Wouldn't it be just a total waste of time to spend a half an hour or an hour checking all the parts in the video amplifier, only to find, which is all living on the neck board, all lives on the neck board in all monitors you work on, except the older Ceronix 1492, Wouldn't it be a shame to spend a whole bunch of time checking the electronics only to find out that the CRT itself is bad? Is everybody with me on what I'm trying to do there? I want to try to not waste time. Remember, that's my big goal, is to not waste any time. Well, there's a couple of ways around that. One is you could actually take the chassis off and try it on a known good CRT. That would certainly tell you if the chassis is good or bad. But there's another real easy way to do this, and it's a really neat trick. This is a pure trick. What I'm about to show you is a pure trick, and it works fantastically well. If you turn in your handout to the next page, page 25, low voltage equals high brightness. And there's a schematic diagram on the next page, and I'm not asking you to so much follow this as if you don't remember what I just said here, this is where you find the information. Here's the deal. Remember that it's the cathode. This is the cathode. I've mentioned that 1,000 times already. This is the cathode, the little round thing that's covered with barium that's in the CRT itself, in the electron gun. Believe it or not, the lower the voltage is on the cathode, the more that gun turns on. The lower the voltage, the less voltage you put on the cathode, the more that gun turns on and the more that color appears on the screen. Huh? What the heck is up with that? Well, that's completely the opposite of everything else in your normal life. It seems totally illogical. Look, think about a light bulb. The more voltage you put on it, the brighter it is. Think about a motor. The more voltage or current you run through a motor, the faster it turns or the more torque it has. If we're talking about a solenoid coil, the more current that runs through a coil, the stronger the magnetic field is. And yet in this case, the less voltage there is at the cathode, the more that gun actually emits. Well, that's pretty weird, but here's why that's true. And it's not so important to know why it's true as the fact that it is true, but here's the reason why it's true. If we look at the electron gun itself, and in fact, let me just show you the electron gun up close. Hang on just one sec. Right on, Frank. All right, so if we look at the electron gun, let's look at a different electron gun. Focus, please. There we go. All right. So we saw this guy before, and this is the cathode. Remember this cylinder part right here is the cathode. And remember, you can see the two heater wires, the heater which runs off of 6.3 volts, that goes into the cathode. So there's the cathode. But right in front of the cathode, there's these other elements. And if I move my hand behind them, you can see the gap there. You can see that there's a gap. So right in front of the cathode, right here, there's this piece of metal, this little piece, a flat piece of metal right here. And then there's this other kind of a sandwich kind of a piece of metal here. And then there's another little flat piece of metal here. There's a big round thing here. And it's a hollow. This is a hollow cylinder. And then, remember I mentioned to you this outside part, which is hooked up to the getter that ends up touching the EHT, the high voltage, right? Well, these are called the grids. These things here, and I'll draw it on the board in just a second. These guys are called the grids. And in fact, you know what I'll do? I'm just going to cut this open. I'm going to break this one apart so you can kind of see what these grids look like. This is what the grid actually looks like. You can see that there are 3 holes in it. The holes to let the electrons out. And there's a grid on the other side. You can see it's just, well, this one's probably easiest to see. It's just a flat piece of metal there with holes in it to let the electrons out. And the one that's right in front of the cathodes looks more or less the same. All right, well, here's what we're looking at, and here's why this is true, that the lower the voltage, the brighter it is. So here's the cathode right here. The heater goes up inside it, and it's covered with that barium stuff. And remember, when the heater, the 6.3 volt heater heats up, it heats up this barium, and it releases the electrons. But as I mentioned yesterday, it only releases the electrons. It doesn't actually shoot them out. The electron gun, it will eventually pick up those electrons and shoot them out, but the cathode doesn't do that. It just lets them go. Right in front of this is the grid. Now, there's several grids in there, and I'm just going to draw one part of it here. It actually is this big, and there's a hole there and a hole there. But let's just draw one gun here. There's a grid in front of this one called grid number 1. But this one that specifically that I'm talking about here, this is known as G2. Grid number 2, grid, G-R-I-D, grid 2. This is the screen grid. It's called the screen grid. Now, it's not a grid like this. When you think of the word grid, of course, you think of that. That's what a grid is. It's not exactly that. It's called a grid because when they first made vacuum tubes, indeed it was a screen that was made of a grid like that controlled the current flow through the vacuum tube. This has the same function, it just has a different shape, so we still call it a grid. It's called the screen grid. Now, you remember when we were talking about the high voltage unit and the main brightness control is called the screen control. I showed you that yesterday. It's the bottom control, the bottom potentiometer on the high voltage unit. And when we turn that up, it controls the brightness of the monitor. What I'm really doing is controlling the voltage on the screen grid. And typically, depending on the monitor, that might be anywhere from 150 volts DC to plus 300, 350 volts DC or something, depending on the physical size of the monitor and who makes it and that kind of stuff. So we're adjusting the voltage on the screen grid. Now, a little bit of a thought experiment here. Just a thought experiment for just 1 second. Remember that opposite polarities attract each other, and we have these little negatively charged electrons. Let's imagine for the moment that the screen grid is at plus 150 volts. And let's also imagine for a moment that the voltage on the cathode, which also goes out to the neck board, this is the CRT socket, that the voltage on the cathode here is also plus 150 volts DC. The front of the picture tube is here. If I have 150 volts positive on the screen grid, it wants to pull those negatively charged electrons this way, right? Because opposite polarities attract. But if I also have plus 150 volts on the cathode, isn't that pulling the electrons this way with just as much strength as the screen grid is pulling it this way? Everybody with me on that? It is, isn't it? So those electrons really are just going to sit there. They're not going to move at all. On the other hand, if I drop the voltage on this, let's make it 0 volts. Let's turn it on all the way. If I make that 0 volts, there's nothing holding it back this way, is there? But I still have plus 150 or 250 or whatever it is pulling them this way, don't I? Therefore, the lower the voltage is on the cathode, the more that gun turns on. So that's the explanation for that. It certainly seems weird, like low voltage turns the gun on. What's up with that? But that's the reason why. And in fact, what we call the video output transistors here are a circuit that is more or less what we refer to as a ground switch. And again, gee whiz, I wish I had 2 weeks to discuss this with you, but I don't. It's a switch that connects to ground. That symbol right there is ground, and ground is 0 volts. Well, remember, a transistor is just kind of like a switch. When this transistor, let's call that the red video output transistor, when it turns on, what's it going to do? It's going to drag the cathode voltage down to ground. Now, there is a resistor here, and there are 3 of them. There's one for each one that goes up to what we refer to as the video B+, which is not the same as the regular B+, but typically it's a somewhat higher voltage called the video B+. And that's what these 3 resistors are here. Not that you really care, you don't, but you'll always see 3 large resistors on the neck board. They're not necessarily all connected near each other, but you'll always see 3 big, large resistors, and they'll always be connected together somewhere, which goes to the video B+. So that's where it gets its voltage to turn off the gun. I know it seems weird, putting voltage on it turns it off, but this is the voltage that turns off the gun. If I have full video B+ on that cathode, it's off. When the transistor turns on, it drags that voltage down to ground, which is 0 volts, and that's what turns the gun on all the time. So the lower the voltage is, the higher the brightness. Now, even if you don't understand that and you can't remember it, that's perfectly okay, because all we're really going to do is use this as a little trick that's going to help us determine whether the problem when we're missing a color is the CRT or the chassis. And the trick is this. If we look at the neck board of the monitor, we can see where the cathodes are. And typically they're in the same spot in almost every monitor. Not every monitor, but typically in most monitors they are. And if you look real carefully on the neck board, you'll see that they're labeled. For example, that's grid number 1, G1. That's actually used as part of the auto bias. You don't really have to know about that. Don't worry about grid number 1. This one's labeled GK. That is the green cathode, GK. K? What do you mean K? Cathode is spelled C-A-T-H-O-D-E. Why are you labeling it K? Well, we label the cathodes with the letter K. And the reason they do that is so you don't confuse G for grid with C for cathode, I guess. It seems stupid. I know what a G looks like, and it doesn't look like a C to me, but there you go. So you'll often find, almost always, that cathodes are labeled with the letter K. Not just in the monitor, but in all kinds of things. So that pin's actually the green cathode pin right there. There's G2. That's the screen grid. G2. That's the one that's got the big voltage on it. These next pins are the heater pins. See, it's labeled, there's the red cathode, RK. The next two pins, 9 and 10, are the heater pins. See how they're labeled H for heater? If I measured the voltage across those two pins, I'd have about 6 volts or so. And there's the blue cathode. So it's real easy to figure out which is the cathodes. Typically, they're labeled. Not always, but usually they're labeled. In some cases, they're not. Like this is a Wells-Gardner board. Thank you very little for not labeling it. But they're still in the same place. Once you know which pin is which, it's, and I can't even remember now, it's 6, 9, and 11, I think. But I'm guessing at the moment. No, it's 6, 8, and 11, because 9 and 10 are the heater. Anyway, so it's not always labeled, but typically it is. Well, the point I'm making here is this. To turn on that gun, all we have to do is ground the black clip lead to the chassis. Remember, we're grounding it, so it has to be a black clip lead. That's real important. And I know the jokes don't work twice. And all we have to do is touch the cathode. So if you observe the front of the monitor in the class here as I touch the cathode and try to do this without damaging anything, and in fact I'm going to just try to play it a little bit safe, which is not what I've been doing so far in this class apparently, but here you go. Focus? Steady, I know. Well, it's hard to do. So there's the green cathode right here, and see the bright green on the screen? As soon as I touch that, it turns on the electron gun. So here's the red cathode. Do you see bright red on the screen? And here's the blue cathode. This is much harder to do than you think. Bright blue, right, on the screen? All right. So is the picture tube good? Yes, it is. So in other words, if I had a problem where I was missing a color, and I didn't know if the problem was in the chassis itself or the CRT, all I have to do is ground that pin, ground the cathode of the CRT, and then I'll know instantly what the problem is. If it lights up, I know the tube is good. If it doesn't light up, or it lights up very dimly, red, green, or blue, I know that the CRT is bad. Tomorrow during the Sencor seminar, Ray will be showing you a really cool piece of equipment called the CR7000 CRT Rejuvenator. I mentioned it to you yesterday, that when you have a weak gun, or in some cases the gun is not working at all, you can often, let me say sometimes, restore that gun back to its normal brightness so that it has proper emission. What we mean by emission is emitting the electrons, of course. But that's a real fast test, and I can't tell you how many times I've used that test. You get to a monitor, it's the only monitor, it's sitting on your bench. I don't really want to grab another monitor down